Hi, and welcome to this video. In this video, we're going to be completing the lecture that we left off at the end of week 6. So we're going to be looking at finishing up our linked list class. That includes finishing our implementation of the iCollection interface, and then we're going to move on to creating our own custom enumerator. So the custom enumerator part is required for your lab 2. So if you have any questions about it after this video, make sure that you send me an email so we can get that worked out. So this project is available for you to download in the week 6 folder. That was our completed project, but we didn't quite get to finish it. We ran out of time. So where we left off was we were implementing all of the different members and methods of iCollection. So the last one that we worked on was working on writing a contains method for our items. Now item is our self-referential class, so this represents one of the items in our list. And I'm just going to open that up for a minute. Our item class here is very simple. The items have a name, and then they contain the pointer to the next item in the list after it. And that's what helps us to maintain our linear linked list, is that each item points to the next one. Now, as far as finding out whether an object or an item is contained within a list, we want to be able to call the list contains method, and it returns a Boolean, true if the item is in the collection and false if it's not. So we perform the iteration, starting at the first element in the list, and then moving to the next one if it doesn't match. Now we wrote a contains method that determines elements are matching if they have the same name. But the slight issue with this is that this comparison here is kind of stepping over the boundaries of what should happen in the list class versus what should happen in the item class. So we've talked a lot about following good practices and the rules for encapsulation that indicate each element should have its own responsibilities. And we've kind of violated that rule here by specifying the comparison method for equality between items. So if I make changes to the item class, it's going to affect how my list class works. And we want to try and avoid that as much as possible. So I'm going to move this over to a different functionality, and it's going to just call the equals method from the item class so that items have control over their own equality comparisons, and we don't have to manually write them out in other classes. So there's just a bit of an organizational shift here away from worrying about the details of what makes one item equal to another. And from here, we're just going to have a call to the equals method. So we're going to write it like this: if current dot equals item, we return true. Now, if they're not equal, we don't want to return false because we want to check the next one in the list. So we have to be careful there that we're getting our logic right. That if we found an equal item, then we're going to return true that the list does contain this item. But we don't want to return false until after we've checked all the items. So that's why we have the return false down here after the while loop. Now, currently, our equals method is coming from object. So we wanted to write our own method for equality because with an object, it looks at the reference. So the two items would have to be the same item in the same memory location in order for equals object.equals to return true. And that might not necessarily be the case. So for example, if we have a list of items A to D, and we're looking for an item called C, it doesn't necessarily have to be the same item. That is, if we're trying to generate an item with the name of C to compare, but the item C in our list has also the next pointer pointing to D, we don't necessarily care about its position in the list, so we don't want to compare the next pointers. So we want to write an equals method that only compares the names. Now when we go into our item class, we want to implement iEquatable so that we can indicate the equality rules between item objects in the item class. So I'm going to implement iEquatable. This is something that we've done before. And I'll just use the shortcut here to implement that interface. So we can write an equals method with an other item. And we can implement this that compares the names by looking at the string equality comparer. So I'm going to return this.name equals other.name. So the logic is the same. In the previous class, we had it written as return this.name equals other.name with the double equal symbol, comparison operator. This is fine too, kind of either one. But this will allow us to, if we down the road decide we want to make changes to how items are compared to each other, we would change it in the item class, and it wouldn't affect the way that the list class works. So we're encapsulating, the logic of how it happens away from the call of when it happens. Okay, so that just finishes up the contains. And now the next step that we're looking at here is our enumerator. Now you might notice that there are two different methods for enumerator. So there's the type safe one, and then there is the not type safe one. So we're going to use the same enumerator for both, and I'm going to start, excuse me, I'm going to start by creating an enumerator class. So because this enumerator is only ever going to be used with our custom list, I'm going to create the class for the enumerator right inside the class for the custom list. So I'm going to nest these classes together. Now it isn't required that they're nested together, but the class doesn't need to be generated for the enumerator unless you have a custom list going. So it's a little bit more efficient that way. So I'm going to create my class called custom list enumerator. Make sure you're putting it in the right place. I'm just going to put it beneath all of the methods in our custom list class here. And we're going to implement IEnumerator, not IEnumerable. And we want to make it type safe. So you can see the interface here, IEnumerator supports a simple iteration over a generic collection. Here we're going to just create the class. Now it's complaining that I haven't implemented this interface, so I'm just going to implement it like this. So the same way that we implemented up above iCollection, now we're implementing IEnumerator. So here's what we get when we implement IEnumerator. We get a current item, so that references the item that we're currently looking at as we're looping through our list. And we have another current here that's inherited from the interface. Dispose, we're not going to pay attention to dispose because we're not going to get into dealing with garbage collection and whatnot. That's a bit above where we're headed. But what we're interested in here is move next, because this indicates how we actually move to the next element. So this is the real point of the enumerator, so that we can move to the next element and then find out what the current element is. Now there's a few different ways that we can make the enumerator work behind the scenes, but the simplest way to do it is to just create an index counter. So what I'm going to do up at the top is just create some more properties. I'm going to create a property that represents the current list. So my list is of type custom list. And then I'm going to create an integer for the index. And last but not least, I'm going to create a private reference to the current item. Now the reason why I'm going to do this is because I want to make sure that the current public item is not able to be manipulated from outside of the enumerator. So we can manipulate this privately. And then our public one is just going to be read-only. So I'm only going to write a get accessor. Excuse me. So for both of these, I'm only going to write a get accessor. Get rid of this exception. So that they can be read-only. Because if we allow outside forces to modify what the actual current item is, then obviously that's going to mix up what order we're going through our list in. Okay, so I'm just going to comment this out so we don't have to see that exception every time our enumerator runs. You know, when it disposes, it will just do its own thing and be killed by the C# garbage collection algorithms. Okay, so we need a constructor. Now that's the one thing this actually doesn't give us, is the constructor that sets up the new enumerator object. So every time we start to enumerate over our list, then we're going to call this constructor so that we are able to start at the beginning of the list, and then we can from there move to the end. And this is part of the reason why you can't manipulate a list and then continue in a for each loop. Because if you remove a particular item, it's going to mix up, you know, what the current item is. And then if you try to move to current.next, but current is already gone, you can see how this is going to be causing problems for us. So I'm going to construct the enumerator by writing a constructor for it. So this is going to create our new enumerator object. So every time we try to do a for each loop on this particular list, then we're going to start here and construct the enumerator object. So we need to pass in a reference then to the current value of the list. And it only happens once when the enumerator starts, so that's why, you know, if the list is modified, the enumerator can't handle that. So my list object that comes in is going to be assigned to my private variable here. And we're going to start our index at -1 because 0 would represent the first item, just like in an array or in any other kind of list. 0 is actually the first element. So before the enumerator starts, index starts before 0. And the element that we're currently pointing to is null. So this here, before the iteration begins. So from there, what we need to do every time a for each loop happens, it moves to the next element in the list. Now we already know how to do this. I'm just going to remove this throwing of the exception here. We already know how to move to the next element because we've done it several times. But the problem here is we don't want to use a while loop because we want to maintain that index. So we have a few things that we can use from our list in order to modify our position in the iteration. And one of those things is count. So if you were to scroll back up, you would see that we have a count property with its implementation. So we'll know how many elements are in the list. And that will help us because we will need to know if we're moving past the end of the list. So our very first thing that we do when we want to move to the next element is increment our index value. So we increment our index value, say the first time it happens, it's going to go from -1 to 0, and that points to the first element. Now, if there are no objects in the list, our list's count would also be 0. And we can't move to non-existent objects. So before we try to actually get into that list, we're going to check to make sure that we're not going past the end. So I'm going to say if my index is greater than or equal to the size of the list, then I can't move anymore. So I'm going to return false. You see how this returns a Boolean if you can move to the next? Here it is. If the enumerator is successfully advanced, return true. Return false if you're past the end of the collection. So we're going to return false in this case. But if we didn't move past the end of the collection, then we need to know where exactly we are moving to and from. So down here, we're looking at starting at the beginning of the list and moving to that position in index. So when we first start our enumerator, index will go up to 0, and we want current to be the item at that 0 position. Now we haven't written an actual item operator yet. That's coming up in a future lesson, but we'll be able to implement the item operator if you had that. So watch for that coming up another time. But for now, what we can do is if we know that, for example, this is our 5th iteration through the loop and index just got incremented to 4. Remember, 0 is the first one, so index 4 would be the 5th one. If index was 4, what we would need to do in order to get to the 4th element is we start at the beginning and just go next, 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 next until we get to element number 4. So that means we need to go next 4 times. So in order to code this, I'm going to start at the first element and move index number of times to the next element. So if we're trying to go to index 5, we need to go .next, 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 .next 5 times. So I'm going to start at the first. To get to the first, I can get it from my enum list. Remember, we have access to that. And because this class is defined within our list class, we have direct access to it. So we have to be careful that we don't modify it. Excuse me. So we're going to start at the first element and skip through using a for loop. X number of times. Just moving to the next element each time until we get to the element at the index that we want. And once we've found that, I'm going to assign it to our local current variable. Once we've finished that, we have successfully moved to the next element, so we're going to return true. So it's pretty simple moving to the next element using iteration. Now the last little piece to reset, if we want to reset our counter, all we need to do is set our index back to -1. So this puts our enumerator back at the beginning of the list. Okay, so our enumerator is complete for now. Now we just need to implement it. So I'm going to just shrink this down. And I'm going to scroll up a little bit back to where the enumerators are called. So now that it exists, whenever we call getEnumerator, we have to return that enumerator that iterates through the collection. So in here, we're going to return a new instance of our custom list enumerator. Now, in our constructor, we need to pass a reference to the current value of the list. But because we're in the list class, what we can do is just pass this. And I'm going to do the same thing in here. To pass the reference to the current list to the enumerator object, the enumerator object saves that, starts the index at -1, and starts the current element to be returned as null. And then, as the enumerator works, it calls on move next to go to the next element, and move next assigns whatever element we're looking at to current. Then, when we call the enumerator to give us the current element, it returns that current value that was set up by move next. And when we're done with the enumerator, it gets called its reset method. So we never actually have to call any of these, but it has to be there in order for each logic to work properly. So now that this is all done, I'm just going to build this up. We're going to go into our main program and make use of this list class. So when we want to create a list of items in our main program, you can see how I've created all the items directly and linked them together. This is a big no-no, so we don't want to have to do any of this stuff. So all of the work that we were doing in here with connecting elements together and inserting them in particular positions and whatnot, we don't want to have to manually do any of that. So I'm just going to comment out all of this stuff. So that we can start fresh. So now our main method, there's a lot of code in here. We're not using any of it. I'm going to go back up to the top so we can code up here. Now we do still have to create some items. So I'm going to uncomment this piece. Just make sure that it's still all commented, the rest of it. So I can create some items, but if I want to store them all in a list, I need to create a new object of type custom list. So I'll just call it my list here, and we'll call its constructor. And since we've written custom list, we know that we can call its various methods. So we have all the same methods that we inherited from iCollection. We wrote some of them were just passed down to us from other, from object class and whatnot. But we can call add and pass in an item to insert to the list. So I'm going to pass in item A, and then we'll pass in item B and C and D. So I'm going to add 4 items to my list, like that. And now we can do a for each loop on my list, because my list has that enumerator that it can pass back to the for each loop. So in order for each to work, my list has to provide that IEnumerable object. So let's do this, console.writeLine I.name. So we can just write out the names of each of the items. So I'm going to run this, and we'll take a look at what we've got for output. You might notice that the items are in reverse order. Now you will know that we can look at our add method to determine how items are added. And you can see that the version of add that I wrote always puts the new element at the beginning. So it is in reverse order because I wrote it that way. If I modify how add works, then the elements would be ordered in a different way, because all we're doing here is calling the .add. And it's up to my list to determine how add is actually going to add the elements together. Then once we get to the for each loop, we can use that enumerator in order to iterate over the for each. So if we didn't implement any of that part, we would, in here, be having an exception. Okay, so that is the end of how to create an enumerator so that you can use a for each loop on a custom list. If you have any questions about this, please send me an email. Otherwise, I will see you next time.